Okay, good morning, everyone. Today we begin chapter number 3, op-amps, one of the most versatile electronic devices that we use in today's devices. Also very powerful, and well, actually, let's bring up the notes and then I'll speak from there. So op-amps stands for operational amplifiers. Operational amplifiers. They are primarily designed from bipolar junction transistors, and they are a version of a differential amplifier. So when we study op-amps, we begin with a little bit of description of the internal workings, not internal work, the internal construction, but not too in-depth. But then from that point on, we will analyze the op-amp as an off-the-shelf part. Okay, so op-amp, operational amplifier, is constructed or is made out of BJTs, the bipolar junction transistors that we saw in chapter 2. It's primarily a differential amplifier, meaning a difference amplifier. But the analysis of the op-amp and the op-amp circuits, we treat the op-amp as a off-the-shelf component. We will look at the basics of what an op-amp is, what it does, and how we can use those, how we can use their properties to design different kinds of circuits. Okay. So first, what I want to say is that the operational amplifier, op-amp, is a differential amplifier. Okay, it's a differential amplifier. It is created by using transistors in a circuit. Okay, transistors in a circuit. And the simplest differential amplifier would look something like this. You'd have two transistors connected, I was going to say back to back, but face to face. Or we can also say back to back. Okay. So this is the most basic version of a differential amplifier. You have two inputs, each at the base of one of those transistors. Let's say this is transistor number 1, and this is transistor number 2. We can call this V in 1, and this can be V in 2. Okay. And this would be RC, the collector voltage, collector resistance for both. This can be RE, the emitter resistance for both. And as always, positive supply and negative supply. And the output, of course, is taken at the collector. So you can say V out 1 and V out 2. Okay. So this is the most basic of difference amplifiers or differential amplifier, created out of two transistors connected back to back, connected face to face, or if you wish, sometimes I also like to refer to it as parallel, connected in parallel, because the emitters of both transistors are connected together and the collectors of both are connected together. The base is open. We apply our AC input signal to the base terminals of both transistors. Now, as I stated, we are not interested, well, in general, we are interested in how a op-amp works, but especially for this class and for this chapter, we are not focused so much on the internal workings, so much as using the op-amp as part of a larger circuit. Okay, so in a typical amplifier basically amplifies any incoming signal. Amplify, the word itself means make it stronger, make it larger, make it bigger. Amplifying, right? Now, signals of all kinds are around us, wired and wireless. Let's take wireless signals, for example. You have wireless signals in the air all around us, right? In the atmosphere all around us. We have cell phone signals, satellite, television, radio, AM radio stations, FM radio stations all around us. Now, those signals, though they are in the air around us, they are very weak, right? They are transmitted wirelessly from a transmitting station that could be tens of miles away, sometimes hundreds of miles away. So wireless signal is weak. When it first comes into our receiver device, that receiver device could be anything, the signal is weak. We perform a little bit of filtering at the front end. Then we need to strengthen that signal and then feed it back into the rest of the circuit. Okay, that's where we would use op amps for filtering as well as for amplification. It can do a 2-in-1 job. Okay, it can filter it out. It can filter out the signals, allow only a specific signal to enter into our device, plus it can amplify the signal at the same time. Okay, so an amplifier functions, basically you have signal amplification and filtering, two of the most important functions. Then you have impedance isolation. Impedance isolation, think of it as, let's say, resistance, right? If you have a system, an electric or electronic system, the input should always have very high resistance or very high impedance, meaning the input side should not load the incoming signal. And the reason is the incoming signal, if the resistance is low, all of that incoming signal will be utilized at the front end itself with very little going into the rest of the circuit. So impedance isolation, what impedance isolation does is it does not load the incoming signal, allows that entire signal to actually go into the rest of the circuit. Okay, and as we go along, you'll learn more about what impedance isolation actually means. In general, we want the input impedance as low as possible. Input impedance, we want it to be as high as possible. And output impedance, we want to be as low as possible. Okay. Again, think back to 201. Those of you who took classes with me, I illustrated an example where we match the output impedance of an amplifier, audio amplifier, to the impedance of the speakers. Okay, maximum power transfer theorem. If you want maximum power to be transferred from one stage of your circuit to the next stage, the Thevenin resistance of both should be equal. Otherwise, most of the current or most of the voltage will be dropped inside. Okay, let's say you have a circuit, and you go a little bit of tangent here. Let's say this is an amplifier circuit, right? And the output impedance is illustrated by this RO. RO. If RO is high, what will happen? This is the rest of the circuit. If RO is high, what happens? Right? It will drop a lot of the signal, a lot of the voltage inside it. We don't want that. We want it to go out of the circuit. Okay. So that is what is meant by impedance isolation. You have an incoming signal to a operational amplifier or an amplifier device. You want it to load as little as possible, meaning do not use up that small signal at the front end. We want it to go inside the amplifier. And in output impedance, we want it to be very low. Amplifiers, of course, are used pretty much everywhere. Audio processing, sensors, filtering, oscillators. Oscillators are function generators. Oscillations to create different kinds of AC functions. Okay, so those are the most common applications. And rather than use discrete components, we can use a pre-built circuit. So think of the op-amp as a pre-built circuit, right? An off-the-shelf part that you take, and then you add certain external components to it, and you can create different functions using that operational amplifier. So this here is the circuit layout of one of the most popular op amps ever. It's called the IC741. The integrated circuit, which has the model number 741. This is also the IC that you use in the lab. This is also the IC that I used as a student more than 30 years ago. Okay, it's worldwide. This is the most common op amp that is used in educational as well as low stakes projects. It's very versatile. It's very popular. It's been around for decades. So its parameters and its functions and its circuits are all very well established. Okay, so you have a large number of components, all on a very small die. A die is a small silicon wafer. And as you can see, there are multiple transistors, multiple resistors, all connected in a circuit design, with the result being that you can take external components and create a new circuit depending on your requirement. The key word is it's a building block. Okay, you take it as an off-the-shelf component and you can create different circuits with it. The op-amp symbol is a triangle, not like the diode. The diode is pretty small. An op-amp, just to illustrate, would have a big arrowhead, typically pointing towards the right. On the left, you have the inputs. And on the right, you have the output. Okay. This is V in negative, and this is V in positive. So we write V in minus and V in plus. Okay. The minus and plus refer to those inputs as being inverting and non-inverting. Okay. Inverting and non-inverting. Inverting in this case means 180 degrees out of phase. What do you notice about the symbol that I drew versus the one that's already in the image? They're flipped. Yep. That's a key thing that students should look out for. Okay. Anytime you look at an op amp, typically you would see the inverting input at the top, non-inverting at the bottom. But that's not always the case. And I speak and I talk about this with experience because I've often made mistakes when I first started learning. It even happens to me right now. I would be in a rush. I'm just skip through the, not looking at all the details. And then I would realize, why is my answer incorrect? Not realize, but I would think, why is my answer incorrect? Why am I not getting the right solution? What is going on? And after 15 minutes, I would realize that the terminals of the given system are actually flipped. So that's something I want students to keep in mind. Okay. Typically, you would see the inverting terminal at the top, non-inverting at the bottom, but that's not always the case. Okay. So we have the inverting input, we have the non-inverting input. The inverting input is basically taking the input signal and creating an inverted image, meaning 180 degrees out of phase. Okay, 180 degrees out of phase. Non-inverting, zero phase, there's no phase inversion or there is no phase transformation. If the input signal is 45 degrees, the output will be 45 degrees. Now, the biggest thing with an op amp is that it has five qualities or say parameters to keep in mind. An ideal op amp will have infinite input impedance, Okay, infinite input impedance, meaning it will not impose any sort of loading effect on the input signal. Second is it will have zero output impedance. And again, the same thing. When you have zero output impedance, the entirety of the output is being transferred out of the circuit. Versus if you have even a little bit of output impedance, some of the signal will be dropped inside. There's infinite differential gain and zero common gain. And I will explain what those mean. And then last and the fifth is infinite bandwidth. Okay, infinite bandwidth. So I'll wait while students write it down, then I'll explain. So the first two I already spoke about, like input impedance, output impedance. We want infinite input impedance as high as possible. And the design of the differential amplifier is such that it automatically occurs. When you have two transistors connected in parallel or back to back or face to face, that's one of the resulting parameters. Okay, so infinite input impedance, zero output impedance, infinite differential gain. Okay, infinite differential gain. And what it means is if you have two input signals going into the negative as well as the positive inputs, the difference between those two inputs will be amplified. At the same time, point number 4, zero common gain, meaning any portion of the inputs at those two terminals that is common will be completely attenuated, completely reduced to zero. Okay, completely attenuated or reduced to zero. Again, the key word is it is based on it being a differential amplifier or a difference amplifier. So it amplifies the difference between the two terminals. Anything that is common at the two terminals is rejected. And that's the biggest positive point about using an op-amp. We have noise signals all around us. Noise in electrical signal simply means any unwanted signal, any unwanted voltage, any unwanted current that we do not want to enter into our system is noise. Okay, so Verizon's signal could be noise for T-Mobile phone because we don't want it to go in there, right? So any unwanted signal is noise. If you have an op-amp and you apply a signal at, let's say, the negative or the positive terminal, for instance, if there are any noise signals around that system, they will affect both inputs at the same time, right? You have an op-amp, it's catching all the signals that are surrounding that system. It will go into the negative as well as the positive input at the same time. So that noise signal will be common to both terminals. The property of the op-amp is that it will reject any common signals. So effectively, it rejects any and all noise signals. And that's the biggest advantage of having this kind of a differential amplifier. Does that make sense? Right? And then, of course, if you take one terminal and you connect it to ground and you apply your input signal to the other terminal, then you're applying a difference between the two. And so now if you have infinite gain for any differential input, you have a very small signal coming into the input that will be difference between the two. amplified to a very high level. And that's the fundamental property of an op-amp. All right, let's take a 10-second pause. Let me know if you have any questions. Any questions? Okay. All right, so here we see V out is AOL, America Online, times V1 minus V2. A, for some reason, I don't know why they chose A, stands for gain of the amplifier. And OL stands for open loop. Okay, A stands for gain, specifically voltage gain. Okay, voltage gain. Voltage gain. So it has infinite open loop gain. Open loop in the sense the output is not connected back to the input. And then the difference between the two, V1 minus V2, is amplified to a very high level. Okay, so V1 minus V2 is differential mode. V1 minus V2 is differential mode, right? So amplifies the difference between the two. And common mode is when V1 equals V2. Noise signals. It will amplify the difference. It will reject all of the noise signals. Yes. Yes. Yeah. Common mode basically, so the question being asked is about common mode. Common mode is basically when the signals applied to both terminals are exactly the same. Okay. So this is the equivalent circuit of an op-amp. Remember, we use a lot of different kinds of analytical models for our electronic circuits. So this is one kind of model that we use for an op-amp. Okay. This is the non-inverting input. This is the inverting input. So non-inverting, and this is the inverting input. The actual input going into the op-amp is VID. VID means the differential input that is going into the op-amp. So it's VI, the input voltage, but it's the difference of the two terminals. So VID, that is what the notation means. And that is given by the difference between V1 and V2. And then the output side, we can model the output side as a voltage dependent voltage source. EE201, chapter 1. This is a voltage dependent voltage source. The triangle illustrates that it's a dependent source, and then the plus and minus signs indicate it's a voltage source. And the dependency is on the input voltage V, right? So the dependency is the voltage V, VID. It's a voltage dependent voltage source. So it supplies an output voltage, but it depends on some other voltage in some other part of the circuit to supply that voltage. So that's a refresher on what a voltage dependent voltage source means. Okay. It supplies VO. So that is the output of that source, but it depends on VID. Okay, so this is just a model. And for this model, we are modeling it as a voltage source, dependent voltage source. So VO is a open loop gain times VID. Open loop gain is typically like tens of thousands. The dimensionless V out over V in. The voltage gain is typically measured in tens of thousands. Now, again, this is just a recap of what I wrote earlier. Ideal characteristics of an op-amp: infinite input impedance, zero output impedance, infinite gain for differential input, zero gain for the common input, and infinite bandwidth. The bandwidth is kind of important because we use op-amps for filtering purposes. So typical op-amps will have a flat gain for a long portion of the frequency response, and then slowly start to decay. So this would occur at very high frequencies. You know what? Let me drive this way. Very high frequencies. So in real life, an op-amp will have infinite gain to a certain limit, and then that gain would start dropping off. But but an ideal op-amp will be a flat line tending towards infinity. Right? Infinite bandwidth, that's what it means. So the portion where the op-amp can actually function at its rated level would be known as the bandwidth of that op-amp. Okay, it would be known as the bandwidth of that op-amp. So again, an ideal op-amp will be a flat line stretching towards infinity. Real life op-amps, it'll start to drop off. Here's another model. You have an ideal op-amp, which has, this is the input side, this is the output side, okay? Just a little bit different rendering. Now in this op-amp, you can see a lot more going on, okay? Inverting input is at the top. Let me mark it out. So inverting input is at the top, non-inverting at the bottom. And then this right here, this impedance represents the input impedance of that op-amp. Okay, so basically the input impedance is the equivalent impedance as seen from those two terminals. And because that is infinite, zero current goes through that branch effectively. Okay, zero current goes to that branch effectively. And at the output side, you should have zero or very low impedance. And so pretty much all of the current that is coming through here should make its way through the output. I would say infinite in that sense. Okay. And because the signal is going into the input inverting terminal, at the output, you would obtain a out of phase, 180 degrees out of phase output. And hence the minus. Minus A indicates inverted output, which basically inverted is 180 degrees out of phase. Okay. So one of the things we do, not we do, but we assume for our analysis purposes is that if there is no current going into the op amp, we say I plus and I minus, meaning the current going into the inverting terminal and the current going into the non-inverting terminal is equal to 0. And if it's equal to 0, then the voltage drop across that resistance or across that input impedance is also 0. Okay, so there are two important concepts that we use or that we assume for analysis purposes. We say that there is 0 current going into the op amp. In reality, a small amount of current will enter the op amp. But again, for an ideal op amp, we say it's as close to 0 as possible. It's 0. Even for a real life op amp, it is as close to 0 as possible. So the voltage drop across that input impedance is very close to 0. And because it's very close to 0, we note that the inverting and the non-inverting terminal are shorted together. And at the same time, funnily enough, we also say that they're open. So we can say the inputs, actually, let me write it down this way. And at the same time, according to our convenience, we can also say the inputs are open. And again, these are assumptions for different models depending on our needs and depending on our purposes. Okay. The key thing here is that if you ground one terminal, one input terminal, the other is also grounded, and we refer to that as a virtual ground. If we ground one of the terminals, whether it's the negative input or the positive input, we can refer to it as being connected to virtual ground, virtually grounded. And again, sometimes we alternate between those assumptions depending on what kind of analysis we wish to do. Okay, so let's take a pause here. Think over all of that and let me know if you have any questions. Yeah. Okay, so let's see. Oh, you're asking about, the question being asked is about whether it's AOL or just A. It depends on the images. So I gathered images from different sources. So one of the books says AOL, open loop gain. In general, we just say it's gain A. That gain specification is part of the manufacturer's spec sheet. Okay, so let's see. How do we use those op amps? Well, we provide feedback. The feedback is basically taken from the output and connecting it back to the input. If you connect it to the negative terminal, we say we are providing negative feedback. If you connect it to the positive terminal, we say we are providing positive feedback. And both kinds of feedback have their own use cases. Okay, so depending on the kind of feedback we use, we can create multiple different kinds of circuits. So negative feedback, obviously, when it says negative, we are talking about out of phase, right? We are providing it into the negative terminal. Negative means out of phase. So it decreases the input that's going in. So you have an amplified output coming from the output, and you take that and you feed it back into the input. So it decreases or inhibits sensitivity to signal variations. If noise is coming into your inverting input terminal, that's a signal variation. You have a signal that's coming in, but you have noise affecting that input signal, then the ability of the op amp is to reject that because of the negative feedback. Okay, so it's going into the inverting terminal and it's being eliminated, or it's being rejected. Okay, there's increased bandwidth and linearity. Now this is not comparing to an ideal amplifier. Okay, ideal amplifier has infinite bandwidth. Real life amplifiers, again, as I said, will start having a slope after a certain frequency range. So when you compare a negative feedback to a positive feedback, the negative feedback has increased bandwidth capabilities, at least larger bandwidth capabilities. Okay. And then, of course, taking from point 1, we have increased signal to noise ratio. So points 1 and 3 are kind of similar, right? If you're rejecting noise signals, then obviously your signal to noise ratio is higher. Positive feedback, all we are doing is we're taking the output and connecting it back to the positive, the non-inverting terminal. And the biggest use case in this scenario is basically using the op amp as an oscillator. And oscillators are building blocks for signal generation. Signal generation. Okay, signal generation. Most of the circuits that we look at will have negative feedback. Okay, so let's take a look at a circuit where we directly take the output and connecting it back to the inverting terminal. Which gives us a circuit. It's a very important circuit, very simple, but very important circuit. It's known by a number of names: isolation amplifier, buffer amplifier, unity gain amplifier, impedance isolator, multiple names, all of which describe this circuit. Okay, all you're doing is simply taking the output of the circuit and connecting it back to the input. Okay, let's talk about the result first. The result of this circuit is that V out would be exactly the same as V in. Okay, the result of this circuit is that V out is exactly the same as V in. Hence the name unity gain amplifier. There is essentially no amplification taking place, but since we're using an operational amplifier, we say it's a unity gain op amp or unity gain operational amplifier. So if V out is equal to V in, then what is the purpose? The purpose is that you can use this circuit to isolate two different circuit systems. Okay, you have pre-amplifier 1 going into the amplifier stage. If you wish to isolate those two, you would insert this circuit in the middle. The reason is that this circuit will have very, very high input impedance and very low output impedance. Okay. And so what it'll do is it'll take the small input signal that's coming in from circuit number 1 and pass it on to circuit number 2 without any loading effect. So it isolates 2 circuits from each other, hence the other term, isolation amplifier or isolation buffer. So isolation amplifier. Isolation buffer. Unity gain amplifier. These are one of the most common names, and one of the most important is voltage follower. Is because the output voltage follows the input exactly as the input is coming in. So anytime you hear the words op-amp voltage follower, this is the circuit that they are talking about. Voltage follower circuit. Okay. And what happens is you provide an input to the non-inverting terminal, amplifies, goes to the output. And when I say amplifies, this is all happening in a split second. Okay. Goes to the output. That output is fed back into the negative terminal. That negative terminal reduces the input going in. So the difference going in is now reduced. Amplifies it again, sends it back to the input. So it's kind of like a loop cycle where the output is not allowed or not permitted to exceed the input. Hence, the output follows the input exactly as it is. So the gain is 1, hence the name unity gain, and the V output voltage follows the input voltage exactly as it is, hence the other name, which is voltage follower. But the biggest advantage of this circuit is that it has very high input impedance and a very low output impedance. So it can be used to isolate 2 different stages of your circuit. Thank you. One thing to keep in mind, we looked at properties of an op-amp, right? We looked at properties of an op-amp. When we create circuits using these op-amps, the properties of those circuits are different from the properties of an op-amp itself. Okay, so if an op-amp has infinite impedance or very high input impedance, then you build a circuit. The circuit itself will also have some properties, as in infinite input impedance or low output impedance. So those would be 2 different things. So again, here, the op-amp in open loop, of course, we say it has infinite impedance, low output impedance, but this now we have created a circuit by taking the output and feeding it back into the input. And this circuit itself also has high input impedance and low output impedance. Okay. One other point, this is not open loop. Output is being fed back to the input. So it's a closed loop. It's a closed loop. One more slide before we get into the other circuits. So most of the circuits that we look at will have feedback going into the negative terminal. So it'll have negative feedback. Negative feedback results in the output being driven low, then being amplified depending on how you connect the circuit components. So when we perform our analysis, again, remember, we are using an op-amp as a off-the-shelf building block, right? The op-amp by itself has some properties. Then you connect a few other components, resistors, capacitors, even inductors to it. Circuit is now different. That circuit itself will also have some properties. So key thing, keep that in mind. They are not the same thing. Okay, so when you perform analysis, we first look at the feedback, whether it's negative or positive. Okay, for the most part, we'll be dealing with negative feedback. So you verify negative feedback. And because it's negative feedback, in one sense, then we assume that V in, the voltage and current, are being forced to zero. Right? You have the out, you have V in coming in to the non-inverting input. Output is going back into the inverting terminal. That inverting terminal, V in and I in, will be forced to zero. So those are assumptions we make. And again, as with diodes and as with transistors, we use our standard analysis techniques to determine the output voltages and output currents. Okay. So it is close to 11. Let's take a break now and then meet back in, let's see, it's 10:57. We've covered a lot of the explanation. Let's meet back in about 5-6 minutes, maybe 11:03, 11:04. In the meantime, if you have questions, feel free to ask.